Hey, what's up, everyone? Welcome to week 2 of learning about neural networks and gradient descents. We're going to be exploring this topic today, and we're going to learn more about it and kind of break it down. What is it really about? So, last week we covered how neural networks actually work fundamentally, but today we're going to be talking more about how they work, but in different parts. So, like gradient descents, cost functions, and all that. So, let's get straight to it. Welcome to the lesson of gradient descent, neural network learning. So we're going to learn about gradient descent today and also about AlphaFold later throughout this lecture. So let's talk about it. But first, let's do a quick recap on what we learned about last week. So last week, we were thinking and learning about neural networks. Speaking of thinking, these guys are basically lots of states and they get activated based on layers. So you have your input layer, then your hidden layers in between that help with biases and weights to determine the output answer. We're going to be expanding upon this idea and talking about more in depth about what actually goes on in these calculations. So, uh, let's start with the classic example of the handwritten digit recognition. Now, you guys might have remembered from last week that we learned about this, and essentially it was just about recognizing specific digits on a 28 by 28 pixel grid, and based on which pixels were um, given a value of 1 or 0 based on light or dark, it was a grayscale image, that would determine what kind of number it was. So that input layer for that neural network consisted of 784 neurons, and each pixel had that grayscale value. We had those hidden layers, just like in this image here, we see those hidden layers. Each of them had 16 neurons, which was an arbitrary number, and each neuron in a layer is connected to all the neurons in the previous layer. Then we had our weighted sum that was passed through a function like a sigmoid or a ReLU. And finally, the output layer has those 10 neurons that represent a digit from 0 to 9, because those were our outputs. Um, Whichever of those neurons were brightest, quote unquote, corresponded to that network's classification. Now, on this very basic example, it will probably work most times. However, there are ways to improve a neural network. One of such ways is called a cost function. So, what a cost function is about is it measures how badly a network is performing. Now, you can kind of relate this to spending money anywhere in the world. You make a certain amount of income, and that income you get tax deductible, and you also, or not tax deductible, you get taxed on it, but you also have to spend money somewhere. So that is your cost function. How much money you need to spend to stay living, say necessary spending. You can consider it like that. So for each training example, the cost is the sum of the squares of the differences between what the network outputs and what we want it to output. A small sum means the network is confident and correct, and a large sum means the network is performing poorly. The cost function takes the network's 13,000 or so weights and biases as an input and gives a single number indicating the performance of the network. So let's quickly move on here. We're going to be learning about gradient descent, which is essentially a cost function. So now that we know the cost function, the higher the sum, the worse the network is performing, the smaller the sum, the better it is. Let's take a look here. Um, so here we have a single input output, and we have a ball rolling down this hill. It looks like a hill, right? There's crevices, there are slopes. And the way to know that uh, this is a good cost function is analyzing the gradient. The gradient is the direction of the steepest ascent, and the negative gradient is the direction of the steepest descent. So ascent and descent. Um, the length of that gradient vector indicates the steepness. But first, let's quickly take a step back and learn about our weights and biases. So to adjust these weights and biases, we use gradient descent. So think of it as a simplified function with one input and output. We want to find the input that minimizes the function. We start at a random input and look at the slope. We shift our input to the left if the slope is positive, and to the right if the slope is negative. Um, and this is where that steepest ascent and steepest descent comes into play. Now the process is the same for a 13,000 dimensional input space. The negative gradient tells us how to adjust each weight and bias to rapidly decrease the cost function. Minimizing the cost function makes the network output something that looks more like the correct answer, and this is how the network learns. The algorithm for computing this gradient is called backpropagation. Each component of the negative gradient tells us two things: whether to nudge the weight up or down, and the magnitude of the change. A neural network with two hidden layers can achieve about 96% accuracy on unseen images. With certain tweaks, it can reach 98%. So it's quite remarkable that a network can learn without us specifically telling it what patterns to look for. We might hope that the second layer of neurons picks up the edges and the third picks up the lines and hoops. That's not exactly what happens in this basic network. The patterns are not what was expected. The network finds a local minimum in 13,000 dimensional space of weights and biases. The network also confidently classifies the random images incorrectly and can recognize digits but does not know how to draw them. This example shows us the limitations of a simple, tightly constrained setup. Now, let's take a step back to go to a different topic for a second here. Let's talk about Google AlphaFold. Now, on the screen here, you see a man by the name of Demis Hassabis. He is the CEO of Google DeepMind, and he got a Nobel Prize for AlphaFold, which is essentially uh, a AI that can detect and learn more about protein structures. But let's quickly learn more about AlphaFold. AlphaFold was created in Google DeepMind, and it started off with learning how to win games like Go. Um, so games are actually a perfect proving ground for AI, as they provide clear objectives and metrics to optimize against. The game of Go is extremely complex, with 10 to the 170 possible positions, making brute force solutions impossible. DeepMind's AlphaGo beat the world champion in 2016 using self-learning. AlphaGo learned by playing millions of games by itself, against itself, and came up with creative strategies. This is only made possible by neural networks, which guides the search processes. With their game AI success, DeepMind moved to real-world problems, including protein folding. Proteins are crucial for all biological processes. They are specified by their amino acid sequence. The sequence folds into a complex 3D structure, like we see here. The question is, can we predict the 3D structure directly from the amino acid sequence? Christian Anfinsen proposed this was theoretically possible by minimizing free energy. This became known as the protein folding problem, a 50-year challenge. The problem is very hard. There are up to 10 to the power of 300 possible conformations for a typical protein. Experimentally, determining uh, determining protein structures can take years of work. Now, what is AlphaFold's breakthrough? Let's start. Well, we have to look back for a second. The context was there was an abundance of data in the protein databank, with about 170,000 protein structures. The CASP competition is a blind assessment to test structure prediction systems. The goal is atomic accuracy, less than 1 angstrom error. AlphaFold 1 improved prediction significantly, and AlphaFold 2 achieved atomic accuracy with a hybrid system that combined evolutionary, physical, and learning components. It also features a recycling stage for iteratively refining the prediction. AlphaFold 2 iterates over many steps to improve its accuracies, and it can fold all known proteins, over 200 million, very rapidly. The AlphaFold database provides free access to these predictions. AlphaFold has an incredible impact across many scientific fields. It helps with new enzymes for tackling plastic pollution It also aids in discovering new mechanisms in reproduction. It is now a standard tool in biology. AlphaFold 3 is able to model interactions between proteins, RNA, and DNA, opening the door for drug discovery. AI systems can find optimal solutions in huge search spaces by using data and models to guide their search. This is exactly why AlphaFold is such an important discovery and creation in our human time and age. DeepMind is also working across the sciences, including medicine, climate, and mathematics. They're working on medical image analysis and diagnosis, and also weather prediction. So now, AI can model patterns and structures in nature, they can model certain types of quantum systems, and so much more. It's a dual purpose technology, but it should also be built responsibly and safely while making these rapid developments. So, in conclusion, today we explored neural networks, gradient descent, and the unexpected ways these systems learn. We saw how these ideas were used to create AlphaFold, revolutionizing protein folding. We know that AI is going to be a transformative technology, and the progress that it's made will have far reaching impacts in the future. So, thanks for joining us on this journey. Thank you for listening and watching. Hope you guys have a good day.